Hello. If you have ever been on call, you may have experienced getting paged by a high urgency alert, proceeding through the runbook, and yet still being able to unidentify the root cause. Novel incidents, or incidents that lack precedent, are often stress-inducing because of the high stakes and the uncertainty involved. My name is Connie. I'm an engineer on the data platform at Rivian and Volkswagen Group Technologies, and today I'm going to cover a novel incident in a critical data pipeline that took days to resolve. So first up, the architecture. Our telemetry data platform architecture is fairly complicated, but for the sake of time, it can be boiled down to this diagram. On the left-hand side, we have the vehicles, which sync their data to a very well-named sync microservice, which then writes the data into a Kafka topic. Then a Flink job will process, standardize, and normalize the data before writing it back into another Kafka topic, where Druid, Apache Druid, will ingest from. Understanding Apache Druid architecture is going to be critical to understanding this incident. And so Druid is an open source distributed time series database with an emphasis on real-time ingestion and query performance, while also maintaining strong guarantees on fault tolerance. Starting with the data plane on the right side, there are middle managers, which are running the task that actively ingest data. In our case, real-time data from Kafka. There are also historicals that serve queries for data that has already been ingested. You can see that the middle managers and historicals actually do not directly talk to each other, but rather both have a connection to deep storage and Zookeeper. This is one of the resilience features of Druid, that data is partitioned into time chunk segments as it's ingested, and those segments must be pushed to deep storage, in our case S3, before the ingestion is committed. So if a middle manager is shut down before it commits offsets, then the next ingestion task will pick up from the previous committed offset, and there will be no data loss. And only after the offsets are committed and data is pushed to S3 is when the segment is broadcast on Zookeeper. Middle managers only run temporary time-bound ingestion tasks, so once a segment has been broadcast, a historical will pick it up from Zookeeper and serve queries on it for the rest of its retention period, whether that's a day, a week, a year, or anything in between. On the left-hand side, we have the control plane components. The coordinator manages the availability of data, ensuring that there are no gaps between when data is ingested on middle managers and when data is available and assigned to historicals. The coordinator is also responsible for managing the number of replicas. So if some data is supposed to have 3 replicas, the coordinator will pick the 3 historicals that are supposed to serve that data and assign the segments to the historicals via Zookeeper. The overlord manages the ingestion of data, ensuring that the right number of ingestion tasks are always running and allocating new segments in the metadata database as they're created by the middle managers. The overlord is the one that will notice if a middle manager task is shut down before its completion time, and it'll schedule a new task to continue ingestion from the last committed offsets. And then in the middle, we have the query layer. The routers are an optional component that can do a bit of load balancing or query tiering, and the brokers are the component that actually execute the query by looking at all the broadcasted segments in Zookeeper and fanning out the query to the appropriate middle managers and historicals that have those segments. And then the brokers are also responsible for consolidating the results. So any group by or order by clauses will be done on the brokers. And the beauty of the Druid cluster is that the whole cluster can be entirely restored with just the metadata storage and the deep storage. Everything else can be rebuilt if it's lost. If a historical goes down, the coordinator will realize that some segments are under-replicated, and it will assign those segments to other historicals, which will then pull the data from S3. Everything is essentially stateless, even though it is all a stateful database. And combined with Kubernetes, it can be even more resilient. Within RVTech, we've deployed Druid on Kubernetes, specifically EKS, using the open source Druid operator. If pods are killed, Kubernetes will bring them back. And then we also get some resource benefits by efficiently scheduling middle managers alongside historicals and also some control plane components onto the same nodes. We're also using RDS for the metadata store and S3 for the deep storage, as I mentioned before. Okay, so a quick recap from our 5-minute crash course on Druid architecture. First, middle managers are responsible for active ingestion and creating the data segments. Second, the historicals are responsible for storing the data segments long term. Third, the coordinator is responsible for assigning segments to historicals and ensuring that data is always available for query. And last, the overlord is responsible for scheduling tasks and allocating segment metadata in the database. So next, what does our observability look like? First, we have a very nice Druid dashboard that's available out of the box with the Druid Datadog integration. There's a lot of information here, but the green and red boxes at the top are a good status summary of how the Druid cluster is doing. Next, going back to our architecture diagram, we have a Canary synthetic that syncs simulated data to the sync service and then queries Druid for the data to make sure that it got through the whole pipeline. The Canary looks something like this. There are 3 steps. The first step is to get an auth token. Second step is to sync some randomly generated data. And the third step is to query for the data and validate that it matches the data that was synced. You can see some of the assertions like the response time should be less than a configure timeout and status code should be 2xx. The last relevant observability metric we use for Druid is the ingestion lag. This is a metric that's published by Druid to represent the difference between the last committed offset in Druid and the high watermark offset in Kafka, which is the offset of the last message published. Now you can see that this peaks at 70 million, which may seem like a huge spike in lag, but the average ingestion rate on this topic is more than 4 million messages per second, so 70 million lag is still less than 20 seconds of lag off the absolute latest. And a spoiler alert, this is what the ingestion lag looked like during the incident. It peaks above 200 billion, which is a few orders of magnitude higher than the normal levels. And so now the incident. The incident started around 2 p.m. Pacific time on September 4th when the first freshness canary alert triggered. Thinking back to the high-level architecture, the priority here is to understand where in the pipeline the data is starting to lag. The canary failure happened at the query layer, but realistically, that could mean that there were breaks in the pipeline in the initial write to Kafka, the Flink job reading from or writing to Kafka, the Druid ingestion, or the query layer. We could also isolate the failure more specifically if there were other alerts that triggered, but at 2 p.m., this is it. So like a binary search, I decided to start in the middle and check the Kafka topic messages per second. This is the Kafka topic that feeds directly into Druid. So if the traffic here is 0, then I know the problem is the Flink job or upstream. And if the traffic here is normal, then the problem is the Druid ingestion or query. So the daily rise and fall you see here is our typical traffic pattern. Because Rivian currently only sells vehicles in North America, there's a strong diurnal pattern where the traffic rises during the day as vehicles are driven and active generating data, and it falls at night when vehicles are generally parked and asleep in the garage. So this traffic is normal, which means that I went to check on Druid ingestion, and here's where I can see a problem. The lag is much higher than it had been previously, but interestingly, there was also a spike in lag yesterday. And the spike from yesterday peaked around 7 p.m., recovered by 10 p.m., but today it started way earlier and has already risen past where the peak was yesterday. And this is when the second alert triggers, specifically pointing at Druid and confirming what I found on the dashboard. So now we've confirmed which part of the system has the issue, and we need to look at what's actually going wrong within Druid. As I mentioned earlier, Druid is deployed on Kubernetes, so I first jumped to the Kubernetes pods overview dashboard. What I can see here is that there are fewer pods than normal, and I also immediately noticed that there was a drop in the number of pods yesterday, which seems to correlate to the lag graph I was just looking at. And when I line them up, I can see that the number of running pods dropped at the same time as when the lag increased the previous day, which is interesting, but maybe more of a symptom than a root cause. And so next, I go to the Druid dashboard and look at the ingestion rate. So the ingestion rate is extremely spiky. It peaks at a very, very healthy 8 to 10 million, but it's unable to sustain that level for more than a few minutes. And the lows are very low, with many minutes passing where Druid is ingesting just 100,000 or 200,000 messages per second. And also on the Druid dashboard, the number of busy threads on the Druid overlord has some correlation with the increase in lag also. And so now I've come up with a primary candidate component of Druid that may be responsible for this issue, the overlord. So I finished going through the runbook. Nothing else really stands out or jumps out, and so I look into the logs. Nothing egregious there. There's some timeouts and a couple errors, but nothing that specifically says how this can be fixed.
Just you're moving on the pack, so just don't.
Okay. I also run some load tests in QA to attempt to reproduce the issue, but No luck. The cluster is much smaller, but I am able to generate a much higher ingestion rate than what we're currently getting in prod. I also check if there's potentially bad data coming in, probably engineering prototypes that are on some experimental version of firmware that could be sending weird corrupted payloads that's throwing Druid off. And I check if there have been any changes in the shape or profile of the data. Maybe there was an OTA rolled out to customers that fundamentally changed what data is being sent. I spend hours chasing down all these possibilities, but they all turn up as dead ends. And so I pull in a couple teammates to brainstorm. So now we're 8 hours in, and here's what we know. The ingestion has slowed down. There's no clear cause given the runbook. The issue is not reproducible, even with a similar ingestion load, although that may point at historical data volume and scale. And the issue does not seem to be caused by external factors like an OTA or bad software on engineering vehicles. And so we have a follow the sun on-call schedule, and it's time for our on-call shift change. So during this handover, the top priority is, while we continue investigating, how can we mitigate the effect on downstream? This is a constant tension during incidents, where you may have a conflict on how much time you spend continuing investigating versus when do you try to take the first mitigating actions to minimize symptoms. How much information do you really need versus taking some action, even if it's not necessarily the ultimate resolution. And so we start brainstorming. Can we scale out ingestion by adding more tasks? But that could add more stress to the overlord, which is responsible for managing these tasks. Should we scale in ingestion by removing tasks? That'll reduce the total throughput, but it might relieve some stress on the overlord. Should we increase the memory limits? The memory usage of the overlord is high, but if the issue is being caused by garbage collection pauses, then this could actually make it worse. And can we set up a profiling tool, memory or performance profiling? And so I'm very action-driven, but I have a teammate that was recommending a lot of caution so that we didn't make things worse. And we needed more information to make the best decision, but since we were already hours into the incident, we wanted to take some action to mitigate the impact. Action versus more investigation. So the lag is bad and getting worse, and we decided to take a two-pronged approach and do both, to continue the investigation while also taking a safe or low-risk mitigating action. And so while a teammate was working on installing a profiling tool in our cluster to continue investigating, I took the lead to increase the memory requests and limits on the overlord. Because we're using the Kubernetes operator, this is a fairly straightforward change, and I was confident I could roll things back if they got worse, and I was also confident the issue is specifically on the overlord. And so this was our low risk or safe action. In the meantime, my teammate was working on installing a profiling tool and gathering more information on what was actually happening on the overlord, coordinator, and middle managers, and that is the more research and investigation part. So then the next morning, now 20 hours into the incident, we regroup. The profiling tool has shown that the overlord is getting stuck on requests in the metadata database, so we turn our attention there. And that leads to our next action. So the CPU was hitting 85% during peak traffic, and we scaled from an extra large instance to a 4x large instance to bring the CPU usage below 30% and eliminate that as a potential cause. And then again, we observed if that change had any effect. At first, the change did seem to help a little, with a slight drop in the lag immediately after we implemented it. But then the lag continued the steady march upwards. But we knew that the issue had something to do with the metadata database and the overlord, so that's where we focused our attentions. And that's how we ended up looking at the Druid metadata table sizes. So you may notice which row is highlighted. We had one table that was 222 gigs of data. The tasks table is used to track the metadata of the tasks, things like the ingestion spec, the current status, et cetera. But it's not actually information that we need after tasks have completed successfully. So can we clean it up? Yes, but we can't just delete things from the database. We need to do it in a safe way. And so we had to think about the best approach to minimize the risk of data corruption. And touching the metadata database is extremely risky because, as I mentioned before, metadata database is one of the two defining pieces of a Druid cluster. So what's the safest way to minimize the risk of data corruption, to stop anything that might be writing to or updating the database? And so we developed this SOP, we tested it in QA, and then we ultimately executed it in prod and observed the outcome. So we do start to see some recovery. And this is the first time that we see significant downward trends since the incident started. And so we kept observing and held off on other actions until the lag started increasing again as soon as the traffic picked up on September 6th in the morning. So now we're entering day 3 of this incident, and we still don't know what the root cause is, but we have narrowed it down to one component, the overlord, and the metadata database underneath. The overlord is still not performing, so we want to take another safe mitigating action while we continue the investigation. In our current state of mind, 2 million messages is better than 0, even if it's not quite the 4 million we need. So we increase the task duration from 2 hours to 4 hours so we can decrease the churn that the overlord actually needs to manage of provisioning new tasks. We reduce the number of running tasks at the same time, and then we observe. And still the lag keeps increasing. So this has long been the highest lag that we've ever seen in Druid, and it only gets worse with every passing minute. And we go back to the table sizes. So the Druid segments table is the other table that has reached the gigabyte level with 42 gigs of data on segments. And when there are multiple tasks that ingest into the same data source in Druid, the overlord must give each segment a unique identifier. So that's a synchronous locking step. And if that request to the metadata database is taking too long, that explains why the ingestion rate is so low. If the overlord takes a minute to respond to a create segment request, then that's a minute where that ingestion task is just not actively ingesting because it's waiting. And that's a good explanation for how the lag could explode so quickly. So we need to clean up the Druid segments table. And now the moment you've all been waiting for, the resolution. This is a much more delicate action than cleaning up the tasks because if we delete the wrong segment data, we've actually caused data loss. And the task metadata is just historical information about what tasks were run and the spec and their status, but the segment metadata is information about where to find the actual data in S3. So we did check and confirm there are some segments that have passed out of retention that still exist in the segment table. And so we have those candidates of what we can drop, but we can't just delete the table because then the data will still exist in S3 and then we'll have no way to clean that up. But Druid actually does have an automated way to clean up metadata because this is a problem that long-running clusters often run into, having performance issues with large metadata tables. Unfortunately, the default settings on this cleanup only kept us going for 3 years before we hit this, but we looked into the documentation and we found the config will have Druid automatically clean up segments when they've passed out of retention and been unused for a certain length of time. And that's the fastest and safest way to clean up segments in Druid and the metadata because it'll make sure to clean up both the metadata and the actual data in S3. So we went back and forth on what a reasonable value would be for these configs, tested for sanity in a lower environment, and then pushed a new config to prod. And then the lag started dropping all the way back to 0. But of course, just because the incident is resolved doesn't mean that the work is done. In fact, we still had quite a few actions to pick up. First, we needed to fine-tune the automatic cleanup config. My whole team and I had been sleep-deprived, desperate to fix, and picked what we thought was the best mix between a conservative, safe config and yet still aggressive enough to actually resolve the issue quickly. But we needed to revisit that config and make sure it was reasonable once we had more active brain cells. Also, there are some proactive alerts that could have been set to warn us about metadata database performance issues before the freshness canary alert triggered. And of course, we needed to document the new SOPs that we had developed kind of on the fly and make sure that if any similar issues happened, that we wouldn't need to spend that time doing the testing in lower environments. And in conclusion, some issues are just not reproducible outside of prod. Prod has historical scale and volume that can't be replicated by running a load test for a few hours or even a day. And in this case, the size of the Druid metadata couldn't be matched by a few hours or even days of load testing in QA, even at the prod ingestion rates. Second, observability saves time and is critical in scenarios where the bug or issue is caused by that scale and it can't easily be reproduced. In a novel incident, there are often many unknown factors, and being able to examine what's actually happening in production is a huge time saver. And in this case, if we had deeper observability into Druid, we may have saved ourselves hours or even days of time triaging. And third, canaries and synthetics are valuable tools that function as early warning signs that something has gone wrong. You can use a correlation ID on the synthetic data so that pipelines that need strictly prod data can exclude them, but you don't know what you don't know, and having synthetics that cover the end customer use case are really critical in incidents like this. And last but definitely not least, ask for help. Incidents and novel incidents, especially, can be stressful and often require many people thinking about the problem from different angles and approaches to get to the final resolution. So don't be afraid to ask for help. And if you like solving complicated problems and building systems at scale, come join us. We have lots and lots of projects coming up in the new joint venture with Volkswagen. We'd be excited to have any of you join. So thank you. Hopefully you learned something, and I'm open for questions.
If you have any questions, there's a microphone on each aisle.
Hey, thank you. This was very impressive. I would love to hear your perspective on AI agents in incident resolution and observability, given the amount of work and complexity involved in resolving that incident.
Yeah, so I was actually really impressed by the demo in the keynote this morning. I don't know if you were there and saw it, but I think that having something like the Bits AI agent that can look at all of these metrics that are in our Datadog instance and kind of correlate them immediately would have helped with especially the initial triage, where I first was looking at a Kubernetes dashboard, then I jumped to the Druid dashboard, and then I had to look at some other metrics around the metadata database. If we could have some kind of agent look at all of that and immediately point out these things all spiked at the same time, which for me it was like I had to remember oh, that also spiked yesterday, 7 to 10 p.m. If the AI agent would be able to do that automatically, I think that would be a huge benefit. I think one of the major factors that added to the time here was actually the fact we didn't have a deep integration with observability within Druid itself. So we didn't have distributed tracing because Druid is an open source software that we just run. We don't have our own really custom image of it right now. And so if we could have had distributed tracing, that would have also been very much faster to point at this is the specific thing that is taking so long in the overlord. But instead, all we could really see is that the ingestion is slow, the ultimate symptom. So I think a little bit more tooling and then an AI agent probably would have helped a lot.
I'm curious how Rivian deals with assessing impact in these scenarios and scaling the response for things like severity, or how did you determine how much to panic and when?
Yeah, very good question. So we're definitely panicking a lot, I think because there are so many unknowns and nothing we were doing really seemed to help for many, many hours. But the impact of this specific incident, I think, is a bit nuanced. It's slightly less customer-facing because the main customer-facing interaction between users and the data platform at Rivian is through the mobile app, right? So you have a mobile app that can show you the current state of charge of your vehicle, if you left it locked or unlocked, all of that. But that doesn't go through this pipeline, right? That's considered a vehicle state, and it goes through a separate data query process. And so this time series historical data is primarily used for reliability, diagnostics, and use cases that need to query the data over more length of time and not just get the latest state. And so there was a lot of urgency, I think, because we pride ourselves on having a very, very low latency of freshness of getting the data into our data platform and having it queryable. But the end customer impact is not quite that severe for this specific incident because it's not end customer facing. So we, about halfway through the incident, did start to have conversations about should we spin up a new cluster? Should we provision a new Druid cluster? It's on Kubernetes. It's fairly straightforward to do that. We just need to add some nodes, provision an RDS database, provision S3 bucket, and then we can just start sending data to the new place. But yeah, we decided to keep pursuing the root cause in the existing cluster because once you spin up a new cluster, then the query layer needs to have some logic of like, if it's after this point, go query the new database. If it's before this point, go query the old database. If it spans that gap, then you need to query both. And so to save ourselves the dev time, we just continued trying to fix the existing cluster.
Hi, I work for a company that also ingests a ton of data from aerodynamic machines. So I've been there. I've had this situation happen multiple times. Have you ever worked with the Datadog's data streams monitoring at all?
No, I
No
haven't.
experience with that. Okay, just curious.
Sorry.
Your thoughts on it?
Hello. During the incident, how did you handle communicating to your internal customers? Did you use these graphs, or did you have notebooks that explained them, or how did you?
Yeah, so generally all of the engineering teams within Rivian have access to the same instance of Datadog. And so a lot of these graphs could be surfaced directly in Datadog without screenshotting them. But I think the majority of our incident response actually does happen in Slack. And so a lot of the questions about like what's the latest status and the kind of incident response was through Slack.
Cool. And follow-up question, how did you prevent the engineers from messing up your time windows while you're looking at the same notebook in Datadog? Is there a way to lock that?
No, we didn't lock it, but the engineers that were working on this, we kind of all had our own notebooks actually, and we were sharing them with each other.
Thank you.
All right, well, if there's no more questions, I guess we're going to wrap up the Q&A. Let's get another round of applause. Thank you.